In this video, we are going to study continue with some preliminaries in graph theory, and we are going to introduce some notions about connectivity which let us go beyond what is just an edge or an arc and to see how far we can arrive from a node concatenating or joining one after the other several edges or arcs. So first of all, we are going to introduce some definitions that we are going to use along this video. First, we denote a chain by a sequence of nodes starting from B0 up to Bm. We have to note that these numbers needn't to be, they don't are the numbers that we use for enumerating just nodes in the definition of a graph. These are particular nodes that are listed and we are following one after the other. And this is possible if consecutive nodes are connected by an edge or an arc. The first node, the node B0, is the initial node, and the last one, Bm, is the final node. A chain, we say that is closed if the initial and final nodes coincide. So the thing is that the chain, we are going to use a particular to fix in a particular type of chains, which are paths, and are those chains in which we have separate nodes in the middle. The only case in which we can have that there are repeated nodes is either at the beginning or at the end. Next, a loop is, as we said before, is a closed path that is reduced to a single node, right? And it's also interesting for many applications, as it is the case of Eulerian graphs, and is they used to look for cycles, and in which we have that a cycle is a closed path that is not reduced just to a single node, and in these cases these paths are now a cycle. So a loop is just a node connected with itself, and a cycle is a node connected with another with itself by passing through different nodes. And the length of the path is equal to the number of arcs of edges that it contains. We will say that in the case of dealing with weighted graphs, we will see that the length of the path is the sum of the distances. So when determining the paths and cycles in directed graphs, the direction of the arcs must be respected. So we have three different examples in which we have one undirected graph and two directed graphs. So in the first one, in the left one, an undirected graph, we see that there is a loop at node 1 because it's connected with itself, and there is a cycle between connecting nodes 2, 3, 4, and 2. And this cycle can be standing as it is, or 3, 4, 2, 3, or we can also consider another sequence of nodes. In the center, we have a directed graph, and we can see that there is a loop also at node 1, and there's again the same cycle as we have seen before between 2, 4, 3, 2. However, if we move to the right, we have changed the direction from arc 3, 2, and now is 2, 3, and we can see that there's still a loop at node 1, but here there is no cycle. There is a generalization of the notion of adjacency matrix, which is the accessibility matrix. The difference is that instead of connecting two nodes by just an edge or an arc, we are looking to connect two nodes by a path in the graph. So in the accessibility matrix of a directed graph, first is just a square matrix as before, with n times n standing n by the number of nodes in the graph, and we will have 1 if bi is connected by bj by a path in the graph, and 0 if there is not connected by any path. In directed networks, as it's in the case with the adjacency matrix, these needn't to be symmetric. So in the case of the accessibility matrix for a non-directed graph is similar, but here what we have is that if there exists a path connecting bi with bj, we also have a path in the graph that is connecting bj with bi. So as a result, we have something similar what we have in the case of the adjacency matrix, that for non-directed graphs, the result is a symmetric matrix. So if we return to the previous examples that we have of Sakari Karate Club and the game of stone, paper, scissors, laser Spock, what we have is that each node can be reached from any other node. So if we compute the accessibility matrix, in this case, the accessibility matrix will be filled with ones in all the positions. But there are examples in which we can find that the matrix, the accessibility matrix, is not filled with ones. So here we have three different examples with the graphs that we had before. So in the first one, what we can see is that any node can be reached, any node from 1, 2, 3, 4 can be reached from the others, right? We could say that each node, in this case, is different with respect to the case of the adjacency matrix. Each node is reached by itself without the necessity of loops or even of cycles. So what we have is that the block with the first 4 nodes is filled of ones. And since 5 is isolated and cannot be reached from the others, and neither from 5 we can go to the others, we have that 5 can be reached just by itself. So we have a 1 in the position 0, 5, 5, but in the rest of the 5th row and column is with zeros. In the second case, what we have is that from 1 we can go to 2, 3, 4, and 4, but we can, and from 2 we can go to 4, 3, and return to 2, of course, but we cannot from these last 3 nodes return to 1. So what we have is that we cannot complete a full block of ones with these 4 nodes. We just have a block of ones with nodes 2, 3, and 4, and 1 is connected the rest, but not in the reverse sense. And in the third case, what we can have is 1. From 1 we can go to 2, 3, and 4. From 2 we can go to 3 and 4. From 4 to 3, but from 3 we cannot return to any node, other node, and neither for 4 and neither for 2. So what we have is that there are many zeros in the lower part of the matrix, which means that from the nodes with higher number we cannot return to the ones with lower number. And again, the 5 is separated and we cannot reach it from the others. So there are 2 algorithms for computing, for calculating the accessibility matrix. The BFS, the breadth first search, and the DFS, the depth first search. So let's go to see briefly how these algorithms work. So what we have is that these algorithms permit to obtain the rows of the accessibility matrix. What we have to do is to apply one of these methods, and also it's worth to mention that these algorithms work for directed and undirected graphs. So let's go to see how it works, the breadth first search. So we are going to consider that we are in A and we want to see which are the nodes that are accessible from A. Of course, if we are in A, we consider that we can access to A, right? And from A we can go to B, C, and D. So what we are going to do is to list them below as nodes that can be accessible from A, and now we are going to see which nodes can be accessible from B, later from C, and so on. So from B we can access now to E and F, so we include them in the list, and we see that we cannot go farther from E or F, right? So it's like we return from the left branch to the middle branch with C, and with C we can arrive to G and H, and later from G we can arrive to I and J. So we include all of them. So we cannot go farther, and this is the order in which we have visited all the nodes following this algorithm. As we have seen, we are going down with levels, and we are including first nodes at distance 1, later distance 2, later distance 3, and so on. So for the case of that first search, what we do is we start with a branch and we go as far as possible to this branch. So what we do is first we go to B, right? From A we go to B. Later we don't include C and D. We try to get deeper into this branch. So we go first to E, we cannot go further, and we go to F and we can neither go further. So in this case we return to C. And from C, what we go is later to G and H, right? From G to I and J, and later, since we cannot go farther, so what we do is we return and we visit H, right? And once we have visited H, the only thing that we can do is to return almost to the beginning and later to visit D. So if you compare both results, the results are different applying one algorithm or the other. So once we have seen the connections that we can set using paths, we can try to look which are the higher subsets of nodes that can be connected from the nodes that we have in the other case, right? So the thing is that in the case that we have an undirected graph, right, we are going to say that it's connected if all the nodes reach each other, right? So in this case, the accessibility matrix will consist only of ones, right? And again, we can say that if the accessibility matrix is filled up with ones, we can say that the graph is connected. If it's not the case, we can speak about the largest subsets which are connected, which are the connected components of the graph, right? So in the case of directing graphs, we have two notions, which is strongly and weakly connected. So strongly connected means that all nodes reach each other using paths that respect the duration of each arc. But in the case of weakly connected is that if we forget about the directions, we are considering if in that case the graph somehow is still connected. So we are converting our directed graph in an undirected graph, and we see if it's still connected. So in the first case, we are using to the largest subsets of nodes and edges that are strongly connected components, and the same for weakly connected with weakly connected components. So returning to our previous example, what we see is that the graph on the left is not connected since the 5 is isolated from the rest. And we have two connected components, one formed by nodes 1, 2, 3, and 4, and the other case by 5. So here, remember that we are saying that this is the largest subset of nodes that are connected. So we cannot just speak about 2, 3, and 4. We have also to include 1. If we go to the graph in the middle, this graph is not strongly connected again, since nodes 1 and 5 are not accessible from the rest. However, we have 3 strongly connected components. One formed by nodes 2, 3, and 4, because following that cycle we can visit all of them, and 2 others with 1 and 5. Despite from 1 we can arrive to 2, and to 3 and 4, since we cannot return, we have to separate 1 in a different strongly connected component. But if this graph is considered as undirected graph, we are in the previous case, and the connected components of the previous case, since they are coming from a directed graph, they are weakly connected components. And in the final case, what we have is that this graph is neither strongly connected by the following reasons that we have said before. And in this case, this is a limit case in which we have 5 strongly connected components, each one with each node, because we cannot have a pair of nodes that are accessible from the other in both directions. But again, if we are considering this as an undirected graph, we're returning to the first example, and despite the graph is not weakly connected, it has 2 weakly connected components, one with nodes 1, 2, 3, and 4, and the other with 5. And that's all. We are going to continue with studying paths and the shortest path in graphs in the next video.